Good morning, Matrix. We are looking at maths in physics today, and we're going to start off with graphs. And where does graphs come in? Now, when we do physical science, it is because we want to look at the universe around us and we want to explain things and we want to predict things. So, what we're going to do is you are going to do an experiment, and then from that, you will get data. From the data, you will plot it and get a graph. From that graph, you get the relationship, and that relationship we're going to take and put it into an equation. Now, whenever you do an experiment, the first thing is very important. What variables are you using? In an experiment, one variable is changed, right? That's the one that we call independent. And then we measure the other thing, and that is the dependent one. It depends on what we changed, right? But the most important of all is for the results of that experiment to be valid, all variables except that independent and dependent variable must be kept constant. And that is sort of the theme for this whole day. Remember, the other things must be kept constant. Now, if you think, for instance, about Newton's law, we already have Newton's second law, right? We already have the equation. But how did they do that? How did they do that? They started with an experiment, right? And in the experiment, there was an independent, dependent, and a constant. Say, for instance, we changed independent, we changed the F net on an object, and we measured what acceleration that object will be. And we kept the mass of the object constant. So then you applied different forces and measured the A. So you'll get different applied forces, right, in newtons there, and that will give you different accelerations in meters per second square, right? So the experiment gave you data, and from that data, we always plot a graph. We always take the independent one that we changed and put it in the x position, and the one that we measured will go into the other position in the y position, right? Now, when they did that, they got a straight line through the origin. And a straight line through the origin means that F net is directly proportional to A. What does directly proportional mean? It means if I've got a certain F here and it gives me a certain value of A, then if that F increases with a specific factor, let's make it 2F, and you go and look at the A, that A will also have increased with a factor of 2, right? So if it's twice the F, then it's twice the A. They are directly proportional. They increase with the same factor, right? And then, of course, we did the same experiment, but by changing the mass and measuring A and keeping F net as my constant, right? So that was my independent, dependent, and constant. And then you got A inversely proportional to M. So now we had two things. We had A directly proportional to F net and A inversely proportional. And from that, we got our equation equals M times A. Right. But when you have the equation, right, you can also work back from your equation to get the shape of the graphs. And you have to know the shape of the graphs. On the next 2 pages, if you turn the page, you will find the graphs that we use most often in physics. Right, now the first one is the best known one. That's directly proportional, right? If you have a straight line through the origin, then we say things are directly proportional. Now, typically, if they ask you to draw a graph of the energy of a photon versus the frequency of the light, right? Energy of the photon versus the frequency of a light. Immediately, we're talking about E, we're talking about F, and I need an equation. So from your information sheet, you will find E equals HF, and H is Planck's constant. So you know that one is constant. So that tells you E is directly proportional to F. If H is constant and F doubles, it means the right-hand side doubles, and therefore the left-hand side will double. If F increases with a factor 2, then E will increase with a factor 2. Same for decrease. Right, so it's a straight line. And remember, it's through the origin. In the next video, we will look at straight lines that does not go through the origin. Right, we're looking at next one, the energy of a photon. We're looking at energy, but now they are looking at wavelength. And the equation that's got both of them and is E equals hc over lambda. Now here, h is already a constant, it's Planck's constant. And since they're talking about in a vacuum, that tells me that the speed of light in a vacuum, 3 times 10 to the 8 meters per second squared, that's going to stay the same. That is not changing, right? So h and c are constant. And if that one is constant, then E is inversely proportional to wavelength. So if I have to show that on a graph, I will show that by using a hyperbola. The hyperbola indicates the E is inversely proportional to the lambda. But I can do something else. I can take 1 over lambda, right? If I take 1 over lambda as my axis, then that is directly proportional to this whole axis, right? That axis directly proportional to the whole axis. So obviously then we get the straight line through the origin. All right, moving on to more difficult ones. 1, directly proportional to the square of x. Now, if they're asking about kinetic energy and they are talking about an object and they're asking about velocity, right? So we need that equation. And the fact that they're telling me they're working with an object tells me that m is constant. We assume that an object's mass doesn't change during the experiment. So then, if both half and m is constant, it means ek is directly proportional to v squared, right? And for a squared one, we need a parabola. So if I have ek and v, that will be a parabola. But remember, if I put the square on the axis, then that axis is directly proportional to that axis, and we'll get the straight line through the origin. Right, next one. Constant. Okay, guys, this one is actually more difficult because this actually usually require that you understand the theory, right? So here we're asking for the speed of light in a vacuum versus the frequency. Now, immediately you will say there's an equation that says V equals F times lambda, or you can also write it C equals F times lambda. So you will want to say, okay, C directly to F. That would only have been true if the lambda is constant. And lambda is not constant. So we're not talking about that, right? The speed of light in a vacuum. What do we know about speed of light in a vacuum? In a vacuum, the speed is always 3 times 10. So it is a constant, right? So this is more difficult because you have to understand, right? Then we're moving on. Now, we've drawn this basic shapes of graphs, but if that constant was a negative, that graph would have turned upside down. And also just make sure that you use the correct terminology, right? When we are working with inversely proportional, don't use the word indirectly. It must definitely be inversely. Indirectly is something else. If you compare things indirectly, it's A compared to B and B compared to C. So A and C is not directly compared, they're indirectly compared. We're not using that, right? Okay, and then a very last one, I haven't seen them ask it anywhere, but it would be nice to know because you are working with inversely proportional to x squared when you're working with universal gravitational law of Newton. Right, now if they ask you draw a graph of the force of attraction between 2 objects versus the distance between them, you're working with this. Since you are staying in the same universe, the universal constant will be constant. And they are talking about 2 objects. So I assume they are not changing mass. So that's staying constant. And then F is inversely proportional to R squared. Now, if you look at that one, we already had the first one, the one where you had 1 over R, and now we have a new one, and that is 1 over R squared. Right. So the only thing that happened with my parabola is it's sort of tilted to that side. It's not a parabola anymore, but it's much the same shape. It's just tilted a little bit in that direction. Right, so how am I going to use this? Well, if they ask you to draw a sketch graph of the acceleration of an object versus different masses on a frictionless surface with the same horizontal force, and they want an A versus M. Now, it's always y-axis versus x-axis. So here you will have A in meters per second squared versus mass in kilograms. Right. Equation, well, they're talking about force. So the equation I have is F net equals M times A. And what they're keeping constant is the F net. Frictionless surface, same horizontal force means you've got the same F net. So F net is going to be my constant. Right. So what is the relationship between A and M? Now, if it's difficult for you to see like this, you can rewrite the equation to get it F net over M, because then it's very easy to see 1 over M. Or let's just consider F net equals M times A. Say the answer was 8 and that was 4 times 2. F net is constant. It needs to say 8, right? So if this one decreases, let's increase this. If this one increased with a factor 2, what do that one have to do to give the same 8 as an answer? It has to decrease by factor 2, right? So if this one increases by factor 2, that one decreases. This one increases, that one decreases, so that I can get the same answer, right? So if this one is constant, those two are inversely proportional, and immediately I will go with a hyperbola. Right, next one, potential energy of an object versus the masses at a height of 2 on the Earth. Right, now potential energy, and there's M and H. So we're looking at EP equals mgh. And they've already told me H is a constant because they're always measuring at 2 meters. And then I have to draw EP in joules or kilojoules versus mass in kilograms. Okay, and EP and M. H is already constant. Now, what about G? Now, if you are on Earth and you are close to Earth, then that G is a constant 9,8 meters per second square, right? So both G and H are constant, and therefore EP is directly proportional to mass. Straight line through the origin, right? Bigger mass, bigger potential energy. Double the mass, double the potential energy. Right, next one, we're looking at mechanical energy, E mechanical. Right, not many equations on the information sheet with that one, eh? But they're talking about a ball falling versus height. So you have E mechanical in joule versus height in meters, right? Now, what do I know about a ball falling? And they tell us to ignore air resistance. The moment that they tell you to ignore air resistance, then you are working with free fall, right? And what do we know? We know E mechanical is conserved. I have a closed system, right? Only gravity is working on that object, then the mechanical energy is conserved. What does conserve mean? It stays the same, it doesn't change. So it doesn't matter what the height is. Your mechanical energy at every height will be the same. Doesn't matter what the height is, the mechanical energy is the same. But this is always the more difficult ones, because this means you have to understand it's not just using an equation. Right. Moving on to number 4. The power dissipated by a man versus the time, delta T, for a man to do 200 joules. So you've got work done by the man, and that is my constant because it's got a specific value. Now, you have an equation, P equals W over delta T, and the work done is constant. So what is the relationship between P and delta T? They are inversely proportional. So if I have power in watt and time in seconds, they are inversely proportional. I will go with the hyperbola. Right. If you've got a bigger power, then it will take a shorter time to do the 200 joules. If you've got a small power, only a few watts, then it will take a long time to do the same work. Right. Next one, momentum, P versus velocity of an object. So I'm working with P equals mv. An object immediately tells me m is my constant and P is directly proportional to V. So if I've got P and V, P in kilogram meters per second and velocity in meters per second, then they are directly proportional. Straight line, prove the origin. Next, the frequency observed by a stationary. Okay, so we're talking Doppler here. Eh? We've got the frequency of the listener versus the frequency emitted by the source, Fs, that is traveling at a constant velocity towards the observer. Right, let's look at our equation. VL equals V plus minus VL over V plus minus Vs Fs. Right, now we are looking at the frequency heard by the listener in hertz and the frequency emitted by the source in hertz, right? And what do we know? Now, V is a constant, right? We're looking at the speed of sound and we're assuming that is constant. We've got a stationary observer, right? Stationary observer. So the listener is stationary. So listener, no velocity, versus emitted by a source traveling at constants towards the observer. So it's traveling towards, which means there at the bottom, we will keep the minus, and that one will be constant. So what we end up with is this whole thing there is constant. V is constant, V is constant, V source is constant. All of them constant, so therefore that one is directly proportional, right? It multiplies by the same factor or fraction, right? So directly proportional. We will still look at things that don't go through the origin, but here they go through the origin. That whole thing is constant, so that is directly proportional. Right, moving on to the next one. Which one of the graphs below represent the correct relationship between F, the force on a charge, and an electric field E? I'm looking for an equation. E equals EQ, and a charge, that tells me Q is my constant. So immediately F is directly proportional to E, and we are, directly proportional to E, and we're looking at a straight line through the origin, right? Next one, a crate is pulled to the right by a force, right? The force, force does work on the crate as it accelerates, right? It's exerted at a 30-degree angle to the surface, experience a kinetic frictional force, okay? So you are pulling something with the force F and there is a frictional force, but now they only ask you the work done on the crate by the force as it accelerates. Which of the following is the best representation of the work done by the applied force? Not all the forces, only the applied force and the distance. Now for work, I have F delta X cos theta, right? Are they changing the force? No, a force, right? So it's the same force, and they don't say use a different one later. Same force. So that is the same force, so that one is constant. Right, for delta x, the distance moved, they're using the d there, right? And then cos theta, they're not changing the angle, so that whole thing will be constant as well. So that tells me the work done is directly proportional to the distance. So we're talking about number B, straight line through the origin. Right, now we're moving on to something else, and that is how I can manipulate an equation to predict something. Right, we're looking at the relationship between variables. And once again, you have to know, if you look at the relationship between two variables, all the other variables in the equation must be constant. Right. So let's look at the first example. You've got a wave with a wavelength lambda and a frequency f and speed v in a certain medium. And in another medium, that same wave has a length of, so they're changing the wavelength. How does the speed of the same wave, which means same frequency, in a new medium compare with the speed? So they're asking about V. Now, first find the equation. There's one, V equals F times lambda, right? Now, there's two different methods, and I would like you to be able to use both. Sometimes this is going to be the one that will give you an easier answer, and sometimes this is going to be the one that gives you an easier answer. So it's V equals F times lambda. What are they changing? It's the same wave, so it's got the same frequency. So frequency is the constant. Now, two different methods. One method is just looking at the relationships. If V is constant, it means V is directly proportional to lambda, right? Which means if lambda increases with a factor 3, then V will also increase with a factor V. And the new velocity will be 3 times the old velocity. It also increased with factor 3, right? Another way is substituting in. If you've got V old equals that, right? What do we know with the new V? It's got the same F, but it's now got 3 times lambda. Right, 3 times lambda, and then you end up with that, and we want to go back. Now remember, we used to have that was our V old. So now we're taking all the strange numbers out so that we go back to the original equation once again, because that original one was the V old, right? So it's 3 times the old velocity. Next example. When a net force is applied to an object with mass m, the object has an acceleration a. So we're obviously working with Newton's second law. What will the acceleration? Okay, so they're asking about the acceleration. So the first thing I'm going to do is I'm going to rewrite this with a in front so that it can tell me what's happening to a, right? It's easier to see. When the same net force that tells me F net is my constant is applied to different masses. Okay, so let's take the substitution one first. I'll write the equation for the original situation. And now comes the change. The net force didn't change. It was the same net force. So for that one, I'm going to put in the same number. But what happened to the mass? 3 times the mass, right? Now, what do we want to do? We want to go back to our original equation because we knew that was A old. So now I take out at the top, there's nothing to take out. At the bottom, there's a 3 to take out. And I end up with that. And then I'm happy because that is once again A old. So this shows me the new acceleration is a third of the old acceleration. Other way to do that, to say, since F net is a constant, A is inversely proportional to mass. So if the mass increases with a factor 3, then the A decreases with a factor 3, and it's 1/3. Okay, moving on. Let's do that. Mars has a radius of half the Earth's radius and a mass 1/10 of the Earth's mass. A hammer has a weight of W on Earth. What is the weight on Mars? So we're talking about Earth and we're talking about Mars. And it should be obvious for you that we're talking about Newton's universal gravitational law, R squared. Right. And we're talking on Earth first. Right. And we are now going to compare that. And that they call the weight W. Right. Now we're moving on to Mars. Right. Now, we're in the same universe, so G did not change. It is a universal constant. Mass, we've got the same hammer, so let's leave the hammer. That mass of the hammer didn't change, but we moved from Earth being the one object to Mars. And what do we know? Mars has a radius half the Earth and a mass 1/10. So instead of M2, I'm going to put in M2 over 10, 1/10 of the Earth's mass, right? And then we're going to R, and what do you see? Half the Earth's radius. So that is R over 2 and squared. So now, at the top, what do I take out? I take out 1/10. And at the bottom, I take out, well, it's a half, but remember it's squared, so I take out 1/4, right, quarter, and then I end up with G M1 M2 over R squared on its own, which is nice because that was the original W. Okay, what should you remember? If you divide by a fraction, then you're actually multiplying by the inverse. So this becomes 4/10, and that is my original weight. So the answer was C. Right, guys, just two more. First one, an object is dropped from rest, okay, so V initially 0, and falls a distance x, and its momentum is p. So it's talking about p and it's talking about distance delta x, right? Ignore the effects of air friction, okay, so it's just free falling, it's just g. The object of the momentum of the object after it's fallen 2x. Okay, stop the bus. What equations do I have for p? P equals m times v, and we're working with an object, so m is not a problem. M is my constant, right? But they're not talking about v, they're talking about distance or displacement. So I need a new equation that's got the v and the x in there. And you should remember v final equals v initial plus 2. You can say a delta t, or you can even say g delta y, right? Doesn't matter. Okay, but in this instance, it's falling from rest. So that, oh, sorry, I forgot the squares, right? So that squared one is equal to 0 plus 2g, and they put an x for the distance traveled, right? So v final is actually the square root of 2gx, and if I can put it in here, x becomes p equals square root of 2gx, right? Now, this is my basic equation. That is for moving x. Now I have a new momentum. Now, what changed? Did m change? No, m was a constant. Did the 2 change? No. Did the g change? No. Only that x changed, right? So p is directly proportional, if you want to do it the second way around, to the square root of x. So if the x doubles, right, what's happening to p? P is directly to the square root of 2 then. Or you could have done it this way and said m hasn't changed, 2 hasn't changed, g hasn't changed, but there I've got 2x over there. And I have to remove what isn't in my original one, and that is that 2. So this becomes square root of 2 and then m square root 2g delta x. Okay, and obviously it's 2 times the original momentum. Square root of 2 times the original. So the answer will be B. Now, what happened to the P? The P should be somewhere there. Okay, right, next one. 2 bulbs, R and 2R. Now, this is a very interesting question. They're asking you which bulb will glow brighter. And unfortunately, some of you have listened so well in grade 10 that you have a problem with grade 11. Right, in grade 10, your teacher told you, I've got bulbs, and I put them into the circuit like this. And let's call this A and B and C and D. And then she told you something. She told you the bulbs are identical. And then she asked which one is brighter. Which one is brighter? And your answer was easy. You just said, okay, A has got the bigger current, so A is going to be brighter. Now, that was fine for grade 10, but in grade 11, you know a lot more, and you should know that glowing brighter is all about the power, right? Power is how much energy is released per second. If that bulb releases more energy per second, light energy per second, then it's going to be brighter. So it's actually about P and not about I. But you were not wrong in grade 10, because P, you've got an equation that says I squared R. And if they told you the bulbs are identical, then R was a constant and P was directly proportional to I squared. So it was fine. You could have looked at I and determined what happened to P, which is the brightness. So there it was easy. A was in the series part of the circuit. It had the bigger current and therefore it had the bigger power and therefore it was brighter. Right. But now we've moved on. We are in grade 11. So now we are not going to talk about I. They can change the R, right? We're not working with identical bulbs. Now, if they change the R, then immediately I'll say, okay, so they're talking about power. So I need an equation with power, but they're changing R. So I need an equation with P and R. And if you look at your equation sheet, your information sheet, you get two different equations with P and R. And now the question is, which one should I use? Now let's look at the first one. They ask which one is brighter when they are connected in series. Now, what do we know when they're in series? When they're in series, current is constant, right? The same current, if there's 3 amps flowing through this one, that will be 3 amps as well. The current is the constant. And immediately I'm going to choose P equals I squared R, because since the current is constant, I know that P is directly proportional to the R. So the one with the bigger resistance will be the one with the bigger power and will be brighter. So here 2R, it's got the bigger resistance, has got the bigger power, and therefore it will be brighter. Right. But if they ask me which bulb will go brighter when they are in parallel, what do you know about parallel? What is the same for these two? The voltage, right? The potential difference is now the constant. So now I am working with P equals V squared over R, because I have to know everything that I don't want to consider must be constant. So if that is constant, then it means P is inversely proportional to R. So the smaller R will be the one with the bigger power. So now R has got the bigger power, and therefore it will be brighter. Right, I hope you've enjoyed that. In the next video, we will be looking at how do I use the graph once I've got it, how can I use the gradient and the area, and we're also going to look at graphs that are straight lines but are not going through the origin.